Okay, this is another video lecture for Calculus 1, Math 181. This video lecture is for Wednesday, April 8th. And the topic today is LHopitals Rule. Let me write that on the board. Okay, this is the topic for today. LHopitals Rule. This is section 4.4. And what this rule has to do with is it's really a way we can evaluate what are called indeterminate limits. It's a trick we can use to evaluate indeterminate limits. So as an example of a limit we may want to evaluate, let's consider limit as x approaches 5 of x squared minus 6x plus 5 over x minus 5. Let's consider this limit. And if we just naively plug in 5 here, so let's plug in 5 to this limit, we get 5 squared minus 6 times 5 plus 5 over 5 minus 5, and this equals 25 minus 30 plus 5, okay, over 0, and this equals 0 over 0. Okay, this is called an indeterminate. This is called an indeterminate form of a limit. Indeterminate form of a limit. Okay, what do we do in this case? Let's consider another limit. The limit as x approaches 0 of 1 over x over 1 over x squared. Okay, if we also naively plug in x equals 0 into this, plug in x equals 0 into this limit, we get 1 over 0 divided by 1 over 0, which equals infinity over infinity. This is also indeterminate. These are both indeterminate forms of limits. Now, how do we figure out what these limits go to? So we don't know yet what the limit is. Let's consider these two cases. So to go down to the first case, let's go back to the first case. What we can do here is factor, so we can factor this limit. Okay, and this comes out to x plus minus 5 times x minus 1. Okay, right? And this is now x minus 5 downstairs. And these two cancel, and this equals the limit as x approaches 5 of x minus 1. And now if we plug in here, we get 4. We get a value of 4. And so we can evaluate this limit by simple factoring. It's no longer indeterminate. If we go to case 2 here, and what we can do here is we can cancel some things out, right? So we can rewrite this limit as 1 over x times the reciprocal of what's downstairs. It's a simple property of algebra. And we get 1 over, here if we plug in 0, if we cancel these x's, we get the limit as x approaches 0. One of these x's will cancel here. We get the limit as x. Limit as x approaches 0 of x, and this equals 0. So we've determined this limit is 0, so it's no longer indeterminate. Okay. Well, that's nice. But what if I gave you guys a limit? So let me erase this. What if I gave you guys another limit? And this limit is of this form. The limit as x approaches 0 of e to the x minus 1 over x. Okay, let's try to evaluate this limit. If we plug in x equals 0, we get e to the 0 minus 1 over 0. E to the 0 is just 1, so we get 1 minus 1 over 0, which equals 0 over 0. Okay? This is an indeterminate limit. However, in this case, there's no simplification we can do. We can't factor this. We can't simplify it by multiplying by a reciprocal and so on. And so we're stuck. We're stuck with an indeterminate form of this limit, or so it would appear. This is where LHopitals Rule comes in. And basically what LHopitals Rule says is if you have a limit as x approaches a of f of x over g of x, so you have one thing divided by another, and this limit is indeterminate, either equals infinity over infinity or 0 over 0. So let's say you have some indeterminate limit of the form of f of x over g of x. Then what we can do is we can take a derivative of what's upstairs and downstairs separately. So this limit will equal x approaches a of f prime of x over g prime of x. So the way we can evaluate this limit, if it's in the, so let's remind ourselves what this means. If we have the limit as x approaches a of f of x over g of x, and that limit is indeterminate, it's either infinity over infinity or 0 over 0, what we can do is take a derivative of each of the separate of what's upstairs and downstairs separately, take a derivative of each of these functions, and then evaluate the limit, and this will give us the actual value of the limit. Okay, one important note here, this is not a quotient rule, so we're not taking the derivative of f of x over g of x as one thing. We're taking the derivative of each of these separately. So we're taking the derivative of f of x, taking the derivative of g of x. Be careful about that. And the only other condition here is that f of x, g of x must be well behaved. They must be well behaved near x equals a, and g of x, g prime of x cannot equal 0 near x equals a. So these functions also have to be well behaved. There's a caveat around x equals a. We can't have g prime of x equals 0 near x equals a, and these have to be continuous and differentiable around x equals a. So let's see how we can use LHopitals Rule to evaluate a limit. I'm going to consider some examples here. And the first example I'll consider, example 1, is actually this example. That example. Look, this is now an indeterminate limit. Let's see if we can use LHopitals Rule to evaluate it. So if we do that, what we do is we take the derivative. Since this is indeterminate, this limit will be equal to the limit as x approaches 0. Let's take the derivative of what's upstairs and downstairs separately. The derivative of what's upstairs is simply e to the x. The derivative of what's downstairs is simply 1. Okay? And now we can plug in x equals 0. We get e to the 0 over 1. Well, e to the 0 is just 1 over 1, which equals 1. So now we've determined that this limit of this function is actually 1 by using LHopitals Rule. Okay? Let's consider another example. Where's the second example? Let's consider this function, this limit, I should say, limit as x approaches infinity, excuse me, of e to the x over x cubed. Let's consider this limit. Okay, if we try to plug in x into this limit, we get e to the infinity over infinity cubed, which in other words is infinity over infinity. So how do we know what this limit is? What we can do is we can use LHopitals Rule to evaluate this limit. There's no simple factoring or simplification I can do, but I can take the derivative of what's upstairs and downstairs separately. So if I take the derivative of what's upstairs, I still get e to the x, right? If I take the derivative of what's downstairs, I get 3x squared. And now I can plug in my limits. I get e to the infinity over 3 times infinity squared, which is equal to infinity over infinity. What happened? Did LHopitals Rule fail us? It didn't. It's just that we still have an indeterminate form. If you still have an indeterminate form after using LHopitals Rule, you simply use it again. So we'll use it again. Take another derivative of what's upstairs and downstairs. We get e to the x over 6x. Okay, if we plug in x equals infinity into this, we get infinity over infinity. We're still indeterminate. So then we have to do another iteration of LHopitals Rule. We take another derivative of what's upstairs and downstairs separately. So now we get limit as x approaches infinity of e to the x, taking the derivative of what's downstairs, upstairs and downstairs over 6. Okay, now we plug in, we get e to the infinity over 6. Okay, well e to the infinity is infinity. We get infinity over 6, which is infinity. Okay, so now we have our answer. We've finally gotten to evaluate our indeterminate limit, and this limit goes to infinity. In other words, e to the x always grows faster than any polynomial. Exponential functions always grow faster than any polynomial. The moral here is sometimes you need to use multiple iterations of LHopitals Rule to evaluate an indeterminate limit. Okay, let's erase this. We're going to consider one other topic here related to this. I need to go check on something on my computer very quickly. I'll be back in about 30 seconds. I don't want to end the video. So let me come back. I'll be back to you guys in 30 seconds. Okay, I'm back. What we're going to do now is we're going to consider what are called indeterminate products. Again, I'm going quickly because I want to keep these video sizes down because they take a very long time to upload to my YouTube channel. So I want to now talk about indeterminate products. Keep in mind, you guys can always stop my videos and replay parts if some of them don't make sense. Let's suppose we have a case where the limit as x approaches a of f of x equals 0, and the limit as x approaches a of g of x equals infinity, and we're concerned with the limit of the product of those two functions. We're interested in evaluating the limit. So one of these functions goes to 0, one goes to infinity. What's the limit of the product of those two functions? Well, if we plug in our limits, we get 0 times infinity. Okay, this is also indeterminate. This is an indeterminate limit. What's 0 times infinity? 0 should make it go to 0. Infinity should make it go to infinity. Which one wins? We don't know. This is indeterminate. But what we can do, a really clever trick, is what we can do is rewrite this limit as, if you guys remember, f times g can be expressed as f over 1 over g. Or it could be expressed as g over 1 over f. This is just an algebra rule, right? F over 1 over g is f times the reciprocal of 1 over g, which is g. So we can rewrite f times g as f divided by 1 over g, or g divided by 1 over f. So we can think of this limit, for instance, as f of x over 1 over g of x. And now, let me just make this clear what this is. And now this is of the form of we can now use LHopitals Rule. Because now we can think of 1 over g of x as a function in the denominator and f of x in the numerator. So we can use LHopitals Rule to evaluate an indeterminate product. Let's consider an example. So here's an example. This is example 3. Let's say we're trying to evaluate the limit as x approaches 0 of x times e to the 1 over x. Okay, if we simply plug in x equals 0, this comes to 0 times e to the 1 over 0, which equals 0 times e to the infinity, which equals 0 times infinity. Okay? This is indeterminate. What is 0 times infinity? I don't know. But what we can do is use LHopitals Rule. So we can rewrite this function as limit of x and e to the 1 over x. We can rewrite this as limit as x approaches 0 as e to the 1 over x divided by 1 over x. So now we can rewrite it in the standard LHopitals Rule form. And then we can use LHopitals Rule to evaluate it by taking a derivative, right? And let's do that. So now if we take a derivative, this is the indeterminate limit. If we take a derivative of what's upstairs and downstairs separately, what do we get? We get e to the elephant is e to the elephant times the derivative of elephant with respect to x. So what happens up here is we get a minus 1 over x squared upstairs. Okay, so we take e to the 1 over x is e to the 1 over x times the derivative of what's upstairs by the chain rule. That's minus 1 over x squared. Okay, what's downstairs is, we can take the derivative of that, we get minus 1 over x squared. Okay? And then what we can do is we can obviously cancel these things out. Okay? We can cancel these things out. These two things cancel, right? This goes away and that goes away. So this gives me limit as x approaches 0 of e to the 1 over x. Okay, and if I do that, then now plug in x equals 0, I get e to the 1 over 0, which equals e to the infinity, okay, which equals infinity. So we now have evaluated this limit. We had an indeterminate limit, an indeterminate product, and we turned this product into a form of one thing over another, used LHopitals Rule to evaluate this indeterminate limit, and we get infinity. We realize that this limit actually grows to infinity. Okay. I want to do one other case. So this is an indeterminate product. These are all really have to do with using LHopitals Rule. I want to just touch on one other case, and that's an indeterminate difference. Okay, let's consider indeterminate difference. And the way this works is, let's say you had the limit as x approaches a of f of x equaling infinity, and the limit as x approaches a of g of x equaling infinity. Okay, and let's say I want to evaluate the limit as x approaches a of f of x minus g of x. I want to evaluate that limit, okay? And so we plug in x equals a in these limits, we get infinity minus infinity equals what? Okay? What does that equal? This is the age-old question of, if you have infinity, you guys this may have come up in math classes before. If you have one infinity minus another, a lot of people, when they're younger, think, oh, it's just 0. Infinity, like 3 minus 3 is 0. Infinity minus infinity is 0. Well, infinities don't work like that. They work differently than normal numbers. So this is actually indeterminate. This is indeterminate limit. We don't know what is infinity minus infinity. Maybe one infinity is a lot bigger than the other infinity. Okay, so how do we evaluate this? And the way we do it, let's consider an example. The way we do it is we find a common denominator. So here's example 4. Okay, let's write this example down. Let's say I have the limit as x approaches 0 of 1 over x minus 1 over e to the x minus 1. Okay, and I decide to plug in x equals 0 into this limit. I get 1 over 0 minus 1 over e to the 0 minus 1. This equals 1 over 0 minus 1 over 1 minus 1, which equals 1 over 0 minus 1 over 0, which equals infinity minus infinity. Okay, this is an indeterminate limit. Okay, how do we do this limit? Well, what we do is we can actually find the common denominator here of this limit. So this would seem like we're stuck, but we're going to use LHopitals Rule. We first find the common denominator. So what we do is we write this limit as x approaches infinity. I'm going to find the common denominator here. So the way I do this, why don't you guys review your algebra on finding a common denominator. My common denominator is this denominator times the other. Okay, we get e to the x minus 1 minus x over x times e to the x minus 1. Okay, I found a common denominator here. for these two rational expressions. And then I simply add them, so I get limit as x approaches infinity of e to the x minus 1 minus x, all of that over x e to the x minus 1, okay? So this is the same exact limit as this, but I've turned this limit into, I found a common denominator. Now we can use LHopitals Rule. So we will use LHopitals Rule here to evaluate this limit, okay? And I'm going to save you guys, in the interest of time, I'm not going to go through this. It turns out this is a little bit thorny. You have to use multiple iterations of LHopitals Rule to evaluate this limit. This is an indeterminate limit. We're going to use LHopitals Rule, take the derivative of what's upstairs and downstairs separately. If we do that, you guys can go through and verify this, but if you do that, the limit comes out to the limit as x approaches 0 of 1 over x minus 1 over e to the x minus 1. This limit comes out to 1/2. So I'll let you guys, if you guys want to verify that, take multiple, use multiple applications of LHopitals Rule. I believe it's 2 or 3, and you get this limit equals 1/2. Let me just summarize. So we talked about LHopitals Rule. It's basically a way to evaluate limits that are indeterminate. And the way the method works is you think of your limit as a function f of x divided by g of x. You take the derivative of f of x and g of x separately, okay? And that should lead you to be able to evaluate your indeterminate limit. If you use one iteration of LHopitals Rule and it doesn't work, apply it again. Keep on applying it until you get to a non-indeterminate limit, till you get to an actual limit. And then we also use LHopitals Rule to evaluate what are called indeterminate products, where you have the limit of f of x times g of x, which will take some form of like 0 times infinity, which is indeterminate. So what we did is we turned those type of limits into one expression divided by another, so we could use LHopitals Rule. And then we also talked about indeterminate differences, where you have the limit of one function minus another. In a case where that equals infinity minus infinity, that's indeterminate. What you can do in that case is find a common denominator, turn your expression into something that is of the form of LHopitals Rule, then apply LHopitals Rule to evaluate that limit. Okay, well that concludes this video lecture, and that was kind of a whirlwind. I'll see you guys on Wednesday, and we can talk about this topic more and go over practice problems. Thank you.